we'll take our look at the calendar. Apologies for the confusion in the calendar because I missed on Friday, but we swapped it so that the project check-in day was Friday. I got the report from Caitlin and also from Jean, who was on duty in the studio at the time, that people were really working quite hard, but enjoying themselves on the project. So I'm glad that we made some progress on the projects on Friday. Just a reminder, the projects are coming up due on October 27 and October 29. So one of those is a week from today, and the other one is the following Wednesday. Okay, so 1 week from today, the drums are due, and then a week from Wednesday, the pipeline is due. All right. So today we're going to do this trig functions day, and I'm also going to hand you this take-home quiz at the end of class today. And it's the same rules as the first take-home quiz. You're allowed to use an index card with anything on it that you want, but you have to make the index card before you look at the quiz. There's a time limit on this quiz of 40 minutes, so it's a little bit longer than the first quiz that we gave you, but still you can take up to double the amount of time. So it says on the top 40 minutes, but you can take 80 if you are so inclined. And I will collect those from you first thing on Wednesday, okay? And again, the quizzes are one of the few things where you are not allowed to work with each other. We encourage you guys to work together on just about everything, but not this, okay? Any questions on the quiz? All right, so I'll give that out later today. So let's jump in on page 24, the kind of teacher-led part here. The demo is a bit on the long side, so we're just going to try to push through some of this trig review. Can we go to Petru for the summary? Okay, so next class we'll talk about the derivatives of the trig functions. Today we're just reviewing some pre-calculus stuff about trig. Number one references a sketchpad file. We're going to skip that and just fill in this blank here. It says the way to convert between degrees and radians is to use an identity. It says a certain number of degrees is equal to a certain number of radians. Anybody know the one that's kind of reduced as far as possible? Yeah, so pi radians is the same as how many degrees? 180 degrees, that's right. And so just a very, very quick review of what a radian is. The radius of this circle I'm going to call r. You don't need to draw this part. And then I'm going to draw something which is going to disappear in a second, but I could draw, say, for example, another radius there. And then I could look at how long that arc is, just as a straight line distance, even though it's curvy, it's got a length. So would you guys say that the length of that curve is more or less than the length of the radius in this moment? Is the curve longer or shorter than the radius? Longer, definitely longer. Okay, so then we'll get rid of that. And so let's draw like this radius up here. And again, look at the arc. So is the curve longer or shorter? Still a little bit longer, but we're getting there. And so if you buy that we're getting there, then you should also buy that there's probably one magical spot. Maybe I'll make it a little bit further up. One magical spot where the length of the curve is exactly the same as the length of the radius, right? There's one spot in there where it's perfectly equal, and that one spot where they're equal, so then I'm going to put up here r, it's the same length as the radius, that if you happen to be at that one magical spot, then you are looking at an angle which is exactly equal to 1 radian. That's the definition of what a radian is. It's that magical angle which makes the arc the same length as the radius. Is that a question? No. Okay. So important note right here. I'll go to Tyler for the note. Thank you. Number 2, I'll go to Cameron. Okay, so let's fill in a few blanks. So I'm going to start at this line right here, which I'll temporarily draw in purple. So we've got some important angles. The first important angle here is 30 degrees. What's the next important angle in this picture? 90 is way over there. We've got a few in between. So we've got a 45 there and a 60 there, and then a 90 is that one that's straight up, right? And so all we're doing is measuring from the positive x-axis. and for some reason counterclockwise is positive angle measures. So we've got those angle measures, and then there's one that I skipped down here. What's the measure of this angle where you don't rotate at all? 0, so that's good. And now in the other blanks, right next to these blanks we filled in, we're going to put the corresponding radian measures. Anybody happen to know any of these offhand? So 30 degrees is exactly pi over 6, that's right. Pi over 6. What if you didn't know? Well, you could take, for example, let's take this 45-degree one, and we're going to multiply it by the right conversion factor. I think this is what Ryan was talking about earlier. We multiply by pi radians over 180 degrees because, number one, the degrees will cancel, and number two, pi and 180 are exactly equal to each other, which means that fraction has a value of 1, right? Because the top and bottom are equal. So it's legal because I'm multiplying by 1, and then it's just a matter of reducing. How many times does 45 go into 180? 4 times, right? So we just cancel the 45 and the 180, and we get a 4 down there. So pi over 4 radians is the next one. That's pi over 4. And next one up, anybody know it? It's pi over 3, good. And then finally the 90 degree is pi over 2. Oh, this one's wrong. Pi over 3 here, and 90 degrees is pi over 2. So, and then finally the no rotation is no radians, so that's fine. So some people just have these memorized, and if you play with radians enough, they will just become part of you, and you don't need to think about like literally converting every angle into degrees or from degrees into radians. But there is this really nifty thing that a former colleague of mine, Niels Abel, showed me, and he talked about how if you actually do the conversion, you don't need to write this at either, but pi over 12 turns out to be exactly 15 degrees. 15 degrees is the same as pi over 12 radians. Now, we normally don't care about 15 degrees, and I guess I still don't. However, if I put in the 15-degree angle, and again, you don't need to draw any of this in, then we're saying that that's 1 pi over 12, right? And then what's the next angle? Well, the next angle is 30 degrees, which means that this guy must be 2 pi over 12, right? And this next one, which is another 15 degrees, must be 3 pi over 12. And the idea is, I'm going to write these and then I'm going to erase them. 1 pi over 12 is the 15, which we don't care about. That's 2 pi over 12. That's 3 pi over 12. What's the next one? 4 pi over 12. What's the next one? 5 pi over 12. Is it here? It's not here. So I'm going to put it in and say we don't care about it, but you got to fill it in. And the next one is 6 pi over 12. And if you just reduce those fractions, then all of a sudden this kind of chaotic green stuff with all these different denominators and no apparent pattern, it kind of becomes obvious where they came from. They all came from the just pi over 12s, and then we reduced them. So by reducing them, we lose the fact that there's this easy pattern underneath. So this helps some people to really just lay them out. Just go pi over 12s and then reduce, and you'll get to the right answers. So let's get rid of all these guys here. And then we'll talk about some of these coordinates. So for the 0-degree angle, get rid of this too. For the 0-degree angle, this is a unit circle, which means the radius is how much? Is 1. That's what the word unit means. So what are the coordinates of this rightmost point? 1, 0. So far, so good. And now we get to some points that are kind of messy, those 3 in between. Let's jump to the top one. What are the coordinates here? 0, 1, that's fine. But then the other ones are the tricky ones. They involve radicals, right? And so some people just have them memorized, and that's fine. If you go on YouTube, you'll find some tricks for remembering these things. People have nifty ideas. They can start kind of moving fingers around and fill them in. For me, I go back to some triangles. I'm going to draw one in here, which is going to make things a bit messy. What's this angle down here near the origin? That's 30 degrees, right? Because that's that angle, which means that this top angle is how much? Is 60, and that means, well, I guess I chose it to be a right angle down there. And I have just memorized the sides of the 30, 60, 90 triangle. I just know that the side opposite the 30 is 1, and the side opposite the 90 is 2, and the side opposite the 60 is radical 3. So those are the lengths of those 3 sides. 1, 2, and radical 3. But Not really. It's really 1 times some number and 2 times that same number and root 3 times that same number. So they're all just dilations. They're all similar to each other. So I don't memorize it with the x's, but I put it up there because I don't know exactly that it's that triangle without the x's. And then we start filling in some coordinates. So the x coordinate here, the first coordinate, is it the horizontal side, the vertical side, or the diagonal? It's the horizontal, right? And so that first guy right there is a root 3. Kind of. The problem is, it's not root 3, because I have physically put something up here, like without this x, that is a lie to say that this is 2, because that diagonal line is how long? It's supposed to be 1, because it's the radius of my unit circle, which means that what I really need to do is cut all these guys down in size. I need to take half of all of them. Can we buy that? Because that 2 is not allowed to be a 2. It has to be a 1. So I'm going to divide that guy by 2, and therefore I am forced to divide everybody by 2. So let's see if we can divide those guys all by 2, and then we'll be able to fill in some blanks here. Okay, so that means that this guy, which I used to call 1, is actually a half, and literally it is half an inch if the radius of the circle is 1 inch. And then in here, this guy that used to be a 2, I divide that by 2, and I get a 1. And how about this horizontal side? Is root 3 divided by 2. And now we're starting to get some numbers that kind of look familiar if you've done some trig before. Okay, and now we're ready to fill in the blanks. So the x coordinate is the length of the horizontal side, which is a root 3 over 2. So root 3 divided by 2 there. And the y coordinate is how long? It's 1/2. It's that vertical side. And if we skip over the 45-degree angle, what do you think the coordinates are of the 60? It's the same, but just reverse. So that's a 1/2. And that's root 3 over 2. And so that's pretty much everything I know about the 30, 60, 90 triangle. And then I also know exactly that same kind of info for the 45, 45, 90 triangle. And so I'm not going to draw it. We're not going to go through the whole thing. Does anybody happen to remember what the coordinates are? Root 2 over 2. And that's the same for both of them. So by hook or by crook, I need you to be able to get these numbers, right? I'm not going to give you a blank unit circle and say fill all this stuff in, but I need you to be able to fill in whichever ones are important in a particular problem. So so we're not going to fill in any more right now, but you should fill in the rest later on, either like during this class or as part of your homework. And if you just do like a quick Google search for unit circle, you'll find many images that you can use to check your answers. And you can see the ones that we filled in here in blue and red agree with what we put, right? Okay, so that's that. And let's, one more thing here. I want to put one more thing. No, we're going to skip that for right now. Let's go to the next page. And we've got definitions of our 6 trigonometric functions: sine, cosine, tan, cosecant, secant, and cotan. Now let's fill them in. On the unit circle, the sine of any old angle. All right, so your answers here are all going to involve x's and or y's. Anybody happen to know what's the sine of an angle? Yeah, it's the y coordinate. So the sine of any old angle is just the y coordinate. So if you've got a point on the circle that comes from some angle, like the 30-degree angle we just looked at, then the sine of that angle is the y. How about the cosine? Is the x. And then the tangent is y over x. Excellent. These are just definitions here. Okay, if you make the chart the correct way, then the second column is really easy to fill in based on the first. Cosecant is the reciprocal of sine. So this is just 1 over y. And secant is the reciprocal of cosine. So that's 1 over x. And cotan is the reciprocal of tan, x over y. And I just want to point out that in terms of setting this up so that you get this easy reciprocal relationship, you got to be really careful, because it's quite tempting to think that cosine and cosecant, because they both start co, are the ones that are related, the ones that are reciprocals of each other, but that's not how they're defined. So sine goes with cosecant, cosine goes with secant. And when I was in your shoes, I memorized that by just thinking, okay, it's not the way I think it should be. They just don't go together the way I think they should. Okay, moving on to number 4, talks about right triangle. We've got these words that we're going to be using now: opposite, adjacent, and hypotenuse. And in our case, the angle that we're talking about is this guy down here that's marked with a T. So the opposite is the opposite guy, adjacent, hypotenuse. There's a little mnemonic device that some people use to remember which one is which for sine, cosine, and tangent. SOHCAHTOA. So useful if you can spell this word that's made up, but not so useful if you misspell the word. And what this is supposed to tell us is that the sine of an angle is equal to the opposite divided by the hypotenuse. And so I'm going to write that in abbreviated form here: opposite over hypotenuse. Back in the 90s, there was a song called OPP. Anybody remember this song? Yeah? I think I know who it is, but you guys are like way too young to even have heard this song. It was pretty popular back in the day. I was disappointed that it didn't have anything to do with right triangle trigonometry, but it still charted. Okay, cosine, according to this acronym, is adjacent over hypotenuse, so we'll fill that in. And then finally, tangent is opposite over adjacent. And the chart has been filled in so that the second column is the reciprocal of the first. So go ahead and fill in the second column, just using those abbreviations again. Everything is reciprocals. All right. So then moving on to number 4. We've got a bunch of graphs of the trigonometric functions. I'm assuming that sine, cosine, and tangent are fairly familiar to you. There's some basic information that you need to know about those 3 graphs. We're not going to be nearly as concerned with the other 3 trig functions, but the ones in the first column are the primary ones for us. So you need to know that sine and cosine just oscillate up and down forever, just like they're pictured here. That the height is 1 and minus 1, right? That's the extreme. And that the length of the horizontal distance before it starts repeating is how much? Is 2 pi, and that's called the period. It's how long until it repeats. And the last piece of info that you need is to know like where they start. Now I know they go forever both directions, so start is not the greatest word, but if we're looking at the y-axis, then I can call that my starting point. And your choices are top, middle, and bottom. Where does sine start? Is in the middle. And is it on its way up or down? Up, right? Because it could have gone that way, but it doesn't. So you need to know that sine starts in the middle and is on its way up. Where does cosine start on the y-axis? Top, middle, or bottom? It's at the top, and then clearly headed down. And then tangent, you probably don't know as well, but anyway, here's the graph of the tangent function, a few periods anyway. And then the other trig functions are graphed at the bottom row. And then we can take a look at 6, which asks us to recall some facts about these functions. Lots of letters around the basic sine function or the basic cosine function. And so each of these letters means something. So I'm going to fill in some words here, and then we'll figure out which letters represent what. So we need to figure out what the amplitude is. We need the period. We need the horizontal shift. And we need the vertical shift. Okay, amplitude. Amplitude is a measure of how far the trig function is stretched from its middle. Which of those letters represents the amplitude? Is A. One little persnickety detail. If A was like -2, would you say the amplitude is -2? It's 2. So technically, yeah, so make it absolute value, right? Just a little detail. Okay, for sine and cosine, what is the normal period? It's 2 pi. So I'm going to start with 2 pi, and then we have to adjust it. Does anybody know which of the letters in here, A, B, C, D, which is the one that affects the period? It's the B. And how do I update the period here? It's 2 pi divided by B. That's good. All right. Finally, one of these letters is the horizontal shift and the other is the vertical. Which one is horizontal? C. So we'll fill in C. And then the vertical shift is D. Another little technical detail. Note that there's a minus sign built inside the parentheses and a plus sign outside the parentheses. What that means is that the numbers that are inside the parentheses kind of work the opposite way you might expect, and the numbers outside work the regular way you might expect. So if you saw something like sine of x plus 4 plus 5, so I can say that there's a plus 4 kind of horizontal shift and a plus 5 vertical shift. Plus 5 vertical would say which way? If I said go plus 5 vertically, you'd go up 5, and that's correct. If I said go plus 4 horizontally, what would you normally, like if it were intuitive, and I said go in the positive x direction, you'd go to the right. But because that minus sign is built into this formula, the things inside the parentheses are backwards. So this is actually left 4, okay? All right, and we call both of these guys sinusoidal functions. So don't feel like you're trapped. If I say write a formula for a sinusoidal function, it doesn't mean you have to use sine. You could use cosine if that's more natural, if it's easier for you, all right? Okay, and then last problem here before the activity is 7. We'll go to Kevin.
A rabbit population varies slightly between 3,000 and 5,000. In 1990 and 2000.
Keep going.
All the population of rabbits as function reduced.
Okay, so we're looking for a formula that will capture the data that we're given here. I can't do any of these problems without a good picture in front of me, so I'm going to start with a good picture. So it says that the max was how much? 5,000. So max is 5,000 and the min is 3,000. So I'll just put some hash marks at those two numbers on the y-axis. And then it says t is number of years, but it's number of years since when? Since 2000. So 2000, we know that in the year 2000 we had 5,000 rabbits, but the year 2000 is what value of t? 0, right? Because years since 2000. So t equals 0. We had 5,000 rabbits. We can plot that point. T is 0, 5,000 rabbits right there. And then the other point we want is this 1990. What is t for that year? -10. And how many rabbits? Was also 5,000. So we'll put -10 pretty much any old place out there. And then another dot on that one. Alrighty. Now sometimes my first attempt at a picture is not very good. I didn't quite get the fact that most of the action was happening there in the top left, and so I kind of smushed stuff, so I'd probably redraw it at this point, but I think I'm happy with it as it is right now, so we'll just draw. And the other fact is we know that we're going to bottom out at 3,000, and that's going to happen halfway between, right? And so we're drawing this kind of a thing here. And now I think we're ready to start asking questions about that graph. So I'm going to fill in the same stuff we did before: amplitude, period, horizontal shift, and vertical shift. Okay, let's start with the bottom, vertical shift. We got to go to the midline. 4,000 is the vertical shift, because normally sine and cosine are centered around the x-axis, right? And that's not the center anymore. The center is right here at 4,000. So that's our vertical shift. Super. I'm going to put, what am I going to put? I'll put plus in there just to indicate we're up 4,000. Okay, let us now jump to the amplitude. Amplitude is how far you stretch from the middle. How far do we go from that middle? Is 1,000. So the amplitude here is 1,000. It's tempting to say 5,000. You say, oh, amplitude is the maximum. It's not true. Amplitude is how far from the middle. And if the middle has moved, you don't get to just grab the maximum. Is that okay? Yeah. All right. And then the period. What is the period? Yeah, so the period. Did I write something untrue in the last one? I think I wrote it correctly before. So what is the period here? The period is 10 years. So I'm just going to put 10 years here, and then I'm going to say, wait a minute, I don't actually need the period, I need B. And so here's another formula that many of you know, is that the period is 2 pi over B. That's what we wrote last time. And so this is the simple equation we need to figure out to get B. So it turns out B is 2 pi over 10, which we can reduce to pi over 5. Okay, and then finally the horizontal shift. Okay, so this now depends on what kind of a trig function we're imagining here. We can imagine it as sine. We could imagine it as an upside down sine function. We can imagine it as cosine or an upside down cosine. If again, I think of the y-axis as my starting point, this guy, where does it start? Top, middle, or bottom? At the top. And which of our nice trig functions starts at the top? Is cosine. And so if you choose cosine, then how much do you have to shift horizontally? Nothing at all, 0. Because we made a really wise choice, and that was to use cosine. So putting all this stuff together, I think we can come up with a formula. I'll call it P of t equals. Now we're just basically using the patterns from the bottom of the previous page. The first thing we wrote there was A, which represents what? Amplitude. So then we're writing our amplitude here. The first thing is 1,000. Then which trig function did we use? Cosine. So we write cosine. And then the next thing we got to put in is the B value, which we found was pi over 5. And I'm going to put in stuff that we don't really need, but just to be super clear, t minus the horizontal shift, which was 0. And then finally plus k, which was the vertical shift, or plus d, I think it was, which is 4,000. So we go plus 4,000. So that's our formula. Any questions on putting all the pieces together? Okay, so now that we've got our formula, we can use it to answer a variety of questions, including part B. During what year and month will the rabbit population next be 4,500? When will the rabbit population next be 4,500? Okay, so the population, is that T or is that P? That's P, right? The population is P. So then basically I'm going to write that purple equation again, but a 4,500 where the P is. 4,500 equals all that stuff over there. 1,000 cosine pi over 5. I'm going to stop writing the minus 0. Okay, so far, so did I miss a zero? I think I did. Should be 1,000 in the front. Okay, so now we got some work to do. The first step is to get cosine by itself. So I've got two 1,000s that need to move out of the way. How do we move the first one? So subtract 1,000, so it becomes 3,500 equals. Thank you. 4,000. Let's try that again. So if we subtract 4,000 from both sides, so that gives us a 500 over here. Okay, and then we move the next 1,000 by dividing. So 500 over 1,000 reduces to just a half. All right, now the fact is, there actually are some nice angles that are on the unit circle that we just marked up where the cosine is exactly a half. Can you guys find an angle where the cosine is a half, remembering that the cosine is always the x coordinate on the unit circle? So which angle that we filled in has an x coordinate of a half? Is this 60 degrees or, wait, 60 or 30? It's the 60, and that's pi over 3, right? Yeah. So one answer is 60 degrees, but we got to write it as pi over 3. And then we could find other answers on the unit circle. But the fact is, most of the time, we're not going to get lucky like this. So we need to make sure we know how to do this on a calculator as well. And I think I heard somebody over here. What's the right tool to get rid of cosine? Is inverse cosine. So we're going to take the inverse cosine of both sides. And that's going to be the thing that gets rid of the cosine on the right. Okay, make sure your calculator is in degree mode. In fact, this might be an issue that you have every time you step into this classroom immediately following physics, is that I think a lot of the time in physics you're in degree mode, and when you walk through that door you change your calculator to radian mode. Everything we do is radian mode. So we should get some messy number here. What do we get? Super. If you type in what we know the answer is, we know the answer is supposed to be pi over 3. If you type in pi over 3, you'll get exactly that. Every single digit on the calculator will agree. But like I said, most of the time it's not nice numbers. So the calculator and the inverse trig is usually where we'll end up. Okay, so that's fine. And then we can multiply both sides by 5 over pi. Okay, and somebody can give me a decimal over here too. Although it might, is it just a nice number now? That seems funny to me. What is it? 1.6 repeating. And that repeating part is because it was really a nice number. This is really 5/3. But usually it's not. Usually you just get a decimal. So 1.6, meaning 1.6 years from 2000, right? So that's like 2001, somewhere in 2001. But we want the next time when we're going to be at 4,500. And 2001 is still way in our past. So we're going to repeat, right? We know that it's going to hit this magic 4,500 rabbits over and over again. So we just got to go back to our picture and hope we can figure out what the answers are. So 4,500, let's see, is halfway between the 4,000 and the 3,000. So I'm going to mark my 4,500 spot here. And draw this dotted thing. And anytime that dotted thing hits our red curve is an answer. There's infinitely many answers to this problem. We just found one of them. So we found one of them was right here. This was our 1.6 repeating. And then there's another one. And we got to be able to use the symmetry of our picture to find that other one, because the calculator will never give you anything other than 1.6, well, other than this 1.070472 on this problem. So we know that it's 1.6 here to here, yes? Which by symmetry, if we go from here to the end of the first cycle, then it's also 1.6. What is the number that gets you to the end of that cycle? What was the period here? It was 10 years, right? Every 10 years we get to the end, which means that this guy right here must have been 10 minus the 1.6 repeating, right? So that's 8.3 repeating, which is in the year 2008, which is still in the past. So we go again a little farther down the road. What's the next one? It's 11.6, right? Just to add that 1.6. So the next one is at like 11.6 repeating, which is 2011. We're getting closer. And then finally, 20 would be the end of another cycle. We go 1.6 in and we land on 18.3 repeating. So in the year 2018. That's the next time. So 2018, and so the 0.3 repeating means 1/3 of a year, right? So April, January, February, March. I guess April is the 4th month. So something like that. Okay, sorry the demo was so long today, but hopefully it wasn't, I don't know if it was painful. There was a lot of reviews, so maybe it was painful. Anyway, see how far you can get through the group activities. I think it'll keep you pretty busy through the end of the class, and raise a flag if I can help.